Okay, so hello everyone. I'm going to talk about two things. The first one is the geometry of ordinary transport, which has been studied by very good mathematicians before, and also the geometry of Gromov-Wasserstein, which is what I'm studying with François Xavier. So let's start with the optimal transport. So just to talk about the basics of optimal transport, so I'm going to consider two measures, mu0 and mu1, probability measures on Rn. The goal is to transport mu0 onto mu1. So we want to transport mu0 onto mu1 in the best way possible, and by best way I mean the least costly way possible. So we can just formulate the Monge optimal transport problem, which is just finding the map phi, which is going to minimize the total cost of sending mu0 onto mu1. So this formulation is very nice, but it has some issues. The first one is that if we want to send one Dirac onto two Diracs, this is not feasible by map. So kind of hints towards finding a relaxation of this problem. We want to be able to split the mass of the first measure. So we're going to use something which is more general than just mass. We're going to use transport plans, which is just generalization that can split the mass. And mathematically, it's just a probability measure on the product space. So this is the relaxation of the Monge problem, which is the Kantorovich problem. It's exactly the same optimization problem, except we minimize for the set of transport plans. A nice thing to remark is that this problem is completely linear in P, so it's a linear program, so it's very easy to solve computationally. So when we do this, when we relax the optimization problem from the set of maps to the set of plans, so we consider a more general optimization problem. And one big question is, can we say that the solution of the Kantorovich problem on transport plans is actually a map? We have the famous Brogniew's theorem, which is states that if mu0 has a density, then there is a unique solution to the Kantorovich problem, and it is a map. And more than this, it's actually the gradient of a convex function. So this kind of justifies the study of the Monge problem as a proxy for the Kantorovich optimization problem. So this is what we're going to study in the rest of the talk. I'm going to also assume that everything is very smooth. So I'm going to consider smooth probability measures that have a density with respect to the Lebesgue measure. So this is what I call dense. And so I'm going to formulate what I call the smooth OT problem, which is the Monge problem, but with smooth maps. So I'm going to work with the diffeomorphisms. And so the set of diffeomorphisms that send mu0 onto mu1, I'm going to call this C of mu0, mu1. It's a set of feasible maps. And we want to find the best map among this set.
Yeah. To be super explicit,
yeah.
Like the Brogniew's theorem and all that, they hold when you use a squared within distance.
Yeah.
Compute the cost.
Yeah. Yeah. So you have all of this. I'm going to use the squared Euclidean distance to compute the cost from x to y. We have also a generalization of the Brogniew's theorem, which is called the twist condition on the cost function c. Which is just the injectivity of the gradient of C. And if we have this, we also have the existence of an optimal map. But in the rest of the talk, I'm going to only use like the squared Euclidean distance.
Like when you just use a distance, it doesn't work because gradient is a distance.
Yeah, exactly.
But if you use like x as a polar.
Yeah, indeed, yeah. Okay, so the question I'm going to try to answer during this talk is, can we recover the classical results of optimal transport theory, for instance, Brogniew's theorem and also the Benamou-Brognier functional, for instance, with kind of a nice geometrical picture. So I'm going to start right away. So I'm going to consider the diffeomorphism group. We can kind of consider this group as Riemannian manifolds of infinite dimensions. I'm not going to go into details of on how to like what's an infinite dimensional manifold, but let's keep the finite dimensional intuition for this talk. So if it's a manifold, what are the tangent spaces? We're going to say that the tangent space at the diffeomorphism phi is kind of the set of translated vector fields. So it's the set of V composed with phi, and V here is a vector field. So this is what I'm going to call phi dot. And the metric we're going to put on diffeomorphisms is the simplest one possible. It's the L2 metric. So if we have a phi dot, which is a tangent vector, we can just integrate the square norm of phi dot against mu O. And this is exactly the same as integrated the vector field V against mu, where mu is the push forward of mu O by phi. So just because I know some of you are familiar with the LDDMM in the room, so the main difference between this and LDDMM is that this is not a right invariant metric. It's only right invariant by the action of the volume preserving diffeomorphism. So I'm going to talk a bit more about this later. So once we have the metric, we can just look at the geodesic equation. It happens that this metric is flat, so we have a very simple geodesic equation. It's just like a linear interpolation between the two diffeomorphisms. We can also formulate it as follows on the right. It's the implicit Burger's equation. And so now we have the geodesics. We can also compute the induced distance. So it's just we compute the energy of the geodesic and we obtain this. And so even now we have one first link with the optimal transport. Let's say that the set of feasible maps, so what I drew in blue on the diagram, let's say that this is this fiber. So optimal transport is simply finding the shortest geodesic between the identity and this set, because we have this equality. OT of mu O mu1 is the minimum over the distance from identity to phi. So actually, optimal transport is just like a geodesic problem, finding the shortest geodesic from the identity to this set. And when we look at the drawing, we kind of have the intuition that the shortest geodesic is going to be kind of horizontal. We want to go from identity and be as quickly as possible to the feasible set. So I'm going to make this precise in the following. So I'm going to introduce a map pi from diffeomorphisms to the densities. It's going to take a diffeomorphism phi, and it's going to give phi push mu O, where mu O is a fixed reference measure. So let's look at the fibers of this map. So the fiber over mu1 is the set of phi that sends mu O onto mu1. So this is exactly the feasible map. And the fiber over mu O is the diffeomorphism that sends mu O onto itself. So it's the diffeomorphism, the volume preserving diffeomorphisms. We can also compute the derivative of this map. And it is as follows. And I do this because I want to say that P is actually a smooth submersion. So when we have a smooth submersion, we can look at the vertical distribution, which is defined at the kernel of the differential. And by definition, this is the divergence-free vector fields. And we can also define the horizontal distribution, which is the orthogonal complement of the vertical distribution with respect to the L2 metric, the metric G that we put on the diffeomorphisms. And we can simply use the Hodge decomposition. Oh, there is a small issue there. We can use the Hodge decomposition and just the integration by part to show that the horizontal distribution is the set of gradients of functions. And this is orthogonal with respect to the L2 metric to the volume preserving to the divergence-free vector fields. So we have a decomposition of the tangent space in diff as the vertical space and the horizontal space. So as I mentioned earlier, the metric on top in diff is right invariant under the action of the fiber of the volume preserving diffeomorphisms. And so this means that we're going to be able to induce a metric on the bottom space, which is actually the quotient of the diffeomorphisms by the fiber of volume preserving diffeomorphisms. And so by doing this, we make P remain in submersion. And the metric we're going to induce on the bottom space on dense is defined as follows. So if we take a small mu dot in the bottom space, which is a tangent vector in the densities, we're going to consider all the vectors in diff that are going to project onto mu dot. We want to find the one of minimal norm. And this is simply the horizontal one. And so as we saw earlier, the horizontal one is the gradient of a function. So the metric we have on the densities, it's by definition this. It's the L2 norm of the gradient of P, where P is linked with linked to mu dot by this equation. And this is simply saying that nabla P projects onto mu dot by the differential of P, of pi. Sorry, I have P and pi. It's not very nice. So we have a metric on the densities. The first question is, what do the geodesic look like in the densities? And we have a theorem for Riemann submersions that say that the geodesics in the densities, and the geodesics in the bottom space are actually the same as the horizontal geodesics in the top space. And as we saw that the geodesics in the top space are just straight lines, we can say that the horizontal geodesics in diffeomorphisms is just of this form, the identity plus t times a gradient. So this is geodesics from the identity, of course. And since we also have the metric on the bottom space, we can just write the Hamiltonian or Lagrangian and do the computation. We can also have this for the geodesics. So the first equation is the continuity equation, and the second one is the Hamilton-Jacobi equation. So this is the geodesics on the densities. And the geodesic distance, which is induced by this metric, is the optimal transport distance. So it's the Wasserstein distance, because we did the computation just before. We have that the distance to identity to diffeomorphism phi is actually the optimal transport cost from u1 to u0. And so what the question we had before, and what we said before, is that optimal transport is just finding shortest geodesic from the identity onto the fiber in blue, the fiber of feasible maps. And so the question we have is, what's the endpoint of the geodesic? What's the map phi1, which is going to be the optimal map for the optimal transport problem? So we just evaluate the geodesics at time t is equal to 1, and we have this formula for the map, and we obtain that it is indeed the gradient of a convex function, of a function. We can also obtain that it is convex by other considerations, but I'm going to just stop there. So we have that the optimal map for the optimal transport problem is the gradient of a function, which is kind of Brownius theorem, so it's very nice. Okay, once we have this, we can also talk about the Benhamou-Grenier formulation of optimal transport, which is also known as the dynamic formulation of optimal transport. So it's a very strong result that says that the optimal transport distance, which is static by definition, minimization on all the transport plans, is actually equal to this. So it's a minimization over all the sets of vector fields Vt and curve mu t on the densities of the energy of the vector field Vt. And so with all these geometrical considerations we had before, it's kind of intuitive that this is true, because this is just finding the curve of minimal energy between mu O and mu1 in the densities, which means finding a horizontal geodesic. So this makes sense. And the usefulness of this formulation is first computational, because with the static formulation of optimal transport, I mean, the static formulation of optimal transport is more costly computationally than solving this formulation, this dynamic formulation. And there is also a theoretical interest to because we can also propose extensions of the classical optimal transport framework. For instance, we can in the continuity equation here. We could, for instance, add a source term on the right hand side, and this kind of leads to unbalanced optimal transport. So this formulation is kind of useful to propose extensions of the classical OT framework. We have this. We can also recover the another nice result, which is the polar factorization of diffeomorphisms, which is due to Brognier. It says that if we have a diffeomorphism, it can be decomposed into the gradient of the function and volume-preserving diffeomorphism. So if we look at the geometric picture on the left, the gradient of the function is just this blue line, and the volume. Then we compose with this phi, which is volume-preserving, and we end up at this phi. So again, the geometrical picture kind of gives this for free. Then we can also do some gradient flows in the densities. So this is the formula for the gradient flow. If you look at the continuity equation I've written there, it's just exactly the same, except the potential P is a very special potential. It's just the derivative of the functional f we want to do the gradient flow with. And one special case of this gradient flow is if we do the gradient flow of a functional which is the entropy plus a potential term. What we obtain when we do the gradient flow is the Fokker-Planck equation, which is the heat flow plus a divergence term. And just as a remark, this equation, the Fokker-Planck equation, is known to converge to its stationary distribution, which is this. And with all this geometrical picture, actually what we have is that the functional f is convex, strongly convex along geodesics. And this implies that we have the exponential convergence of mu to the stationary distribution mu infinity in terms of the KL divergence. So this is also very nice.
Could you re-explain the...
So we have, so the curves in the densities, they are sorry. The curves in the densities are the form this. I don't know if you can see. So this is the continuity equation, and gradient P is the vector on which we use to act on the density. So it's the little tangent vector that's going to be acting on the density and in the bottom space. And what we want to do is we want to choose a very special vector, tangent vector. We want to use one that's going to minimize, go in the direction of minimization of the functional f. And so this is what we do by replacing p by this Fréchet derivative of f. So this is going to point towards the direction which is going to minimize the functional f. Is it a bit more clear? Or?
I was just wondering if we can just say that this is...
Yes, it's exactly this. I mean, it's what I've written in gray. So you can just interpret this as the gradient of, the co-metric of the Wasserstein, the Wasserstein auto metric. This is just a G inverse times the gradient, which is the definition of the Riemannian gradient. But yeah, it's exactly this, yeah.
And maybe a bit of context that, it's very clear, like it's your first example of those gradient flows that motivate the study, that probably are people who say catégories are not very complete. Then if I remember correctly, like if F is, for instance, the entropy of your distribution against the weight measure, then...
So this is exactly what you said, yeah. If F is the entropy, so it's the KL divergence with respect to the Lebesgue measure, then we have the heat flow. The gradient flow is exactly the heat flow. And if we have potential term, then we also have this divergence term, which makes the Fokker-Planck equation. So yeah.
And maybe, you know, from a computational perspective, that's clear for everyone, that this Wasserstein gradient flow is what you get if, you know, you parameterize the probability distribution. You can say, okay, I have a grid, and I have gains, and I have my weights, and I parameterize my measure by my weights. And you say, okay, I make a gradient flow which makes the weights, that's standard gradient flow for electrometric. But instead, you may say, no, and that's what we do in expedition analysis, is that you say, no, I have samples. You know, each sample has a constant weight, one over n, and you make the optimization with respect to the position of the points. And that's exactly what you do when you do Wasserstein gradient flow. And basically what this means is that, for instance, if you have a population of points, and you say that you estimate the density using a Kerman estimator, and then you compute the entropy of your function, and you say, okay, this is my function. I use PyTorch to make gradient descent against the positions of the points, against the position of the point, and you're going to retrieve a heat flow or heat dispersion. But that's, I think, like all of this is really the mathematical framework which is behind making gradient descent with respect to the position of the samples, not with respect to weights. I thought maybe like.
I agree. Okay, and just to summarize what I've said, so we have a Riemannian summation from the diffeomorphism group with the L2 metric onto the densities, and this induces the optimal transport metric. And in this geometric framework, optimal transport is just finding the shortest geodesic from the identity to the constraint set, the feasible set of diffeomorphisms. And actually the shortest one is going to be the horizontal one, which is going to be induced by small gradients of functions. And in this, this framework kind of encompasses a few results. So we have the polar factorization of diffeomorphisms. We have the Hodge decomposition of vector fields, which is actually just of a local version of the polar factorization. If we look at the geodesic equation on the diffeomorphism group, we have the Invisit-Burgers equation. If we constrain it to be on the volume-preserving diffeomorphisms, we have the incompressible Euler equation. And the geodesic equation on the densities is the Hamilton-Jacobi equation with the continuity equation. Also, if we do the gradient flow of the entropy with respect to the optimal transport metric, we have the heat flow. If we add the potential term, we have the Fokker-Planck equation. And also, it's very useful in a lot of different fields. For instance, in machine learning, if we do the gradient flow of functional L, this is kind of the same as training infinitely wide neural networks. And this is the Shiza and Bach paper. So I've done a little table because there are a lot of other subnotions that are very interesting as well. So the first column is what I just talked about. So it's the diffeomorphism group with the L2 metric, which is not right invariant, and this is the Wasserstein geometry. But we could also put a different metric on the diffeomorphisms. For instance, we could put the Sobolev H1 metric, and this would induce the Fisher-Rao metric on the set of densities. If we want to do some unbalanced optimal transport, we have the same idea, except the top space is a bit bigger. We have to add the action of some functions in order to account for the change of mass in the positive densities. So dense plus is just positive measures. GW is Gromov-Wasserstein. I'm going to talk about this just next. And just to make the comparison with LDTMM and metamorphosis, so if I understood correctly, but please do correct me if I'm wrong, the LDTMM framework is the same as optimal transport. You have diffeomorphisms, you put a kind of a L2 metric. You can also have a kernel on the L2 metric, but let's say we don't. Except this time it's right invariant. And then the bottom space could be anything with an action. And yeah, that's it. And the metamorphosis is the equivalent of unbalanced optimal transport in the right invariant way.
Yeah, maybe a question on your table, because the key thing with the LDTMM is that it's L2, but like, or more like N2 or like a symbolic metric with respect to the ambient space. Whereas here, like in your table, like it's L2 underscore mu.
Yeah, right. So it's L2 of mu. Yeah. Okay, and there it's L2 of the Lebesgue measure or the volume measure or something. Yes.
And so, for instance, for like the second column,
Yeah.
it's H1 of the ambient space. Sorry.
Yes. Yes, it's H1 of mu.
Okay, so it's still H1 of mu.
Yeah.
Then also H1 mu, but then on the left side.
Yeah. Yes. Okay. Yeah. Right. Yeah. You're right. And also, I don't know if some of you are working with like positive semi-definite matrices or things like this, because we have the finite dimensional equivalence of the two first columns also. When you restrict the set of densities to only Gaussian measures, you can just parameterize by their covariance matrix, which is a positive semi-definite matrix. And we also have this nice submersion from diffeomorphisms to densities, except now it's from invertible matrices onto positive semi-definite matrices. So this induces the so-called Gromov-Wasserstein metric on the set of positive semi-definite matrices, or the Fisher-Rao metric if you put either the L2 or the H1 metric on diffeomorphisms. Yeah.
It's the kind of stuff that François Xavier is talking about. So here, the metric with respect to the diffeomorphism. So it's what happens when you link points around. But do you remember if, like, okay, if you have a smooth density, and you say, okay, like you look at the distance between the smooth density and the small perturbation.
Okay.
Like, okay, it's mu and then plus the mu. Remember, it's like, if I remember the story that it's like the Wasserstein metric, it's L2 with respect to this displacement, but it's also locally something like h minus 1 of the pointwise.
Okay. Yeah, so this. Wait, where is it? Okay. So if you look at this metric, which is the square norm of the gradient p, you could also write it explicitly in terms of mu dot. So you just take the continuity equation and you invert it, and so you have gradient p is equal to something. And so this is going to be kind of a h minus 1 operator on p, or gradient p, I'm not sure. And so maybe this is what you mean. So this gradient p is the top vector, and this is h minus 1 with respect to this. Does it make sense for you?
Yes, it's perfect. Yes, so I think your paper is really nice. I think it's very good to 5 minutes this way, and probably like to make it super explicit. So that you have this line where it's gradient the metric with respect to phi. And
okay.
That's basically what you've written, and maybe you make it explicit that it's an L2 against which space,
okay,
against which measure. And then, really, like if there was a second row of like what's the equivalent of thing that you respected weights, that's kind of your whole parameterization.
Yeah, when you say the weights, it's mu?
Yes, it's so instead of moving the samples, change.
Yeah. So this is with respect to the weights, it's h minus 1. Yeah, you're right. Okay, I should add a row. Yeah. Okay.